Hello friends, in number system we'll be talking about perfect numbers, the HCF LCM related formulas and some other stuff in the set. So friends, let's first understand what are perfect numbers. Any number is called a perfect number if the sum of all its factors including one but excluding itself is the number itself. So we'll start with an example. Let's take the number 6. Now we write down all its factors, which are 1, 2, 3 and 6, and we exclude itself, which is 6, from the list of factors, and we get just 1, 2 and 3. And we take the sum of these factors, we get 6, which is nothing but the number itself. So that means that 6 is a perfect number. Now let's take another example. We take the example of a number 8. Now for 8, we write down all the factors, which are 1, 2, 4 and 8, and then we remove 8, which is the number itself, from that list, and we take the sum of the remaining factors, which is 7. And since this is not equal to the number 8, so this is not a perfect square, not a perfect number. So we take another example. Let's take the number 28 now. And now we write down all the factors of this number 28. We have 1, 2, 4, 7, 14 and 28. And again, from this list we remove 28, which is the number itself, and we take the sum of all the other numbers. So we have 1 plus 2, 3 plus 4, which is 7. 7 plus 7 is 14, and 14 plus 14 gives us 28. Now this is equal to the number itself, so this is a perfect number. So we have 28 as another perfect number. Now let's look at HCF. So HCF for general numbers, for the natural numbers, we've studied in earlier classes. Now what is the HCF for a given fraction? It is given by HCF of the numerators divided by LCM of the denominators. Say for example, we have to find an HCF of 2 by 5 and 3 by 8. So the final HCF of these fractions would be HCF of the numerator, and that comes out to be the numerator of the final HCF, and we take LCM of the denominators and that put that in the denominator itself. So that comes out to be the HCF of given fractions. So now in this case, HCF of 2 and 3 is 1 and LCM of 5 and 8 is 40. So we say that 1 by 40 is the HCF of these two given fractions. Now the greatest number that divides x, y and z, leaving a remainder a, b and c respectively, is given by the HCF of x minus a, y minus b and z minus c. So we are saying there is the greatest number which can divide x and leave a remainder a, which divides number y, leaves remainder b, and divides z and leaves remainder c. So we subtract a from x, b from y and c from z, and we get three numbers. And if we take the HCF of these three, we get that greatest number which will divide x, y, z, leaving these three different remainders. And another important point for HCF is the greatest number that divides x, y and z, leaving the same remainder, but the remainder is not given. What is the remainder? If the remainder is given, then we can simply subtract that from the given numbers and we can take the HCF of those subtracted numbers. But here we are told that the remainder is same in all the three cases, but the remainder is not given. In those cases, HCF is given by x minus y, y minus z, z minus x, and we take HCF of these three numbers. We get the numbers by x subtracting y from x, z from y, and x from z, and we get these three numbers, and we take the HCF of these three numbers. So now let's see how do we reach this formula that this greatest number can be obtained by receiving HCF of these three. So now let's see that let's assume this greatest number to be h. Now we say that since it divides x and leaves some remainder, so let's say x will become some product k1 into h plus a remainder a. Similarly, y would also be divisible by h, so we can say y is equal to k2, some constant k2 into h plus the same remainder. So now if we subtract y from x, we get x minus y. This remainder, this cancel out each other, and we get this is equal to k1 minus k2 whole multiplied by h. So this means that x minus y will be completely divisible by h. Similarly, y minus z and z minus x will also be completely divisible by this greatest number h. So now using that formula, since we do not know the remainder, these are the three numbers x, y, z is what we know of. This is the approach that we take by subtracting these numbers from each other. So we get three numbers x minus y, y minus z, and z minus x, and we take the HCF of this to get that greatest number, which will divide these three, leaving the same remainder. Let's now look at the LCM. So if we want to find out LCM of given fractions, it is given by LCM of the numerators divided by HCF of the denominator. So say for example we have two fractions, one is 2 by 5 and another is 1 by 15, and we want to find out the LCM of these two numbers. So what we'll do is we'll find out the LCM of the numerators, which is 2, and put that in the numerator, and the HCF of the denominators, which in this case is 5, and put it in the denominator. So we get 2 by 5 as the LCM of 2 by 5 and 1 by 15. Now the least number, which when divided by x, y and z, leaving the same remainder r, is given by the LCM of x, y, z, and we add this r to it, because it is the LCM of x, y, z will divide the number completely, and then if we add r to it, we are saying that will be always the remainder when that is divided by either x or y or z. So the least number, which when divided by x, y, z, leaving the same remainder r, is given by the LCM of the given numbers plus the remainder r. The least number, which when divided by x, y and z, leaves the remainder a, b and c respectively, so it's leaving different remainders in each case, it is given by the LCM of x, y, z minus p, where p is equal to x minus a, which is equal to y minus b, which is equal to z minus c. So we are saying, although it is leaving different remainder in each cases, but the difference between the number and the remainder is always the same. So x minus a should be equal to y minus b, should be equal to z minus c, and that we define as p. So if we find out the LCM of the given numbers and we subtract p from it, that is the least number which will leave the remainders a, b, c when divided by x, y and z respectively. So let's now try to find out the units digit of any number which is expressed as a power of any natural number. Now say for example we take a units number which is expressed as a power of 2. So something like 2 raised to power 4, 2 raised to power 9, or you could say, generalizing it, we can say 2 raised to power a. So now this, if we want to find out the units digit of this, it will always be one of these digits, 2, 4, 6 or 8. Why? Because it always repeat itself in the same order after a power of 4. So we say 2 raised to power 1 is 2, then 2 raised to power 2 is 4, 2 raised to power 3 is 8, 2 raised to power 4 is 16, and now if we go to 2 raised to power 5, it comes out to be 32, where the units digit is 2, which is same as 2 raised to power 1. So now if we continue to see this, say we'll say 2 raised to power 6, and that comes out to be 64, where the units digit 4 is same as the units digit of 2 raised to power 2. So it repeats itself in the same order after a power of 4. 1, 2, 3, 4, and then 5, it comes back to 2. So this is how it is we can find out the units digit of any number which is expressed as a power of 2. Units digit of a number which is expressed as a power of 3, 3 raised to power a. This is any one of these 4 digits, which are 3, 9, 7 and 1, and again it repeats in the same order after power of 4. So if we see, 3 raised to power 1 is 3, 3 raised to power 2 is 9, 3 raised to power 3 is 27, where the units digit is 7, 3 raised to power 4 is 81, where the units digit is 1, and now we come to 3 raised to power 5, which is 243, and the units digit is 3, which is same as the units digit of 3 raised to power 1. And if we continue to do it after this also, we'll see that it continues to repeat it in this order: 3, 9, 7, 1, and then again 3. So this is how we'll find out the units digit of a number which is expressed as a power of 3. And this is the approach which can be taken for any other number, any number which could be expressed as a power of 4, 5. So if we know that what is the sequence that it takes, and after how many of this sequence does it repeat itself, if we observe that sequence, we can find out the units digit of any number which can be expressed as a power of some number. And this is very, very useful. This approach is very useful where we are solving the MCQs, and there are some options. Instead of doing a final product and finally calculating the value of this expression 2 raised to power something, if we just find out the units digit, and we can find out which would be a suitable answer. So these are some of the techniques which are used in speed mathematics. Friends, I hope you enjoyed the session. If you find it useful, please like it and share it with your friends. You can visit us at our Cool Smart Learning website and post your queries there. And please subscribe to the Cool Smart Learning channel for getting updates on the new sessions. Thank you.